Welcome back. In this lesson, we're defining functions. And a function is a special type of relation between two sets A and B. And instead of a capital R, we usually use a little f or some letter like that, a little g, to represent a function, especially if you're in an algebra class. And we don't think of it as a relation on A cross B as much as a function from a set A to a set B. So it's a relation such that for every element in A, there is exactly one pair A comma B, where that, of course, B is an element of B. So if you remember, in relations, AB is an element of A cross B. So this is B is in B. But we don't usually write a function as AFB. We write it as f is a function from A to B. So f goes from A to B. That's our notation, if you haven't seen it before. And we don't usually write that AF is AB is an element of f. We write f of A equals B. So that's how you're used to seeing functions if you've dealt with functions before. So let's let A be the set 1, 2, 3, and B be the set W, X, Y, Z. So we want to create a function from A to B, which means we need to map every element of A to exactly one element in B. So 1 is going to map to W, 2 is going to map to Y, so it's taking care of 1 and 2. We've also got to do 3, so 3 in this case is going to go to W. Why is 1 going to W, 2 going to Y, and 3 going to W? We're just making up a function. So this is just a made up thing for an example. But the point is that everything in A, 1, 2, and 3, each has to be in exactly one pair. So I can't have another pair with a 1, and I can't have no pairs at all with a 2, for example. Everything has to be in exactly one pair. That's what makes this a function. So we can then write this relation f is a function from A to B, and that's our notation. And then it would be defined as f of 1 equals W, f of 2 equals Y, f of 3 equals W. Notice that they can map to the same element. Doesn't matter. F sends 1 to W and 3 to W, that's okay. And it sends 2 to Y, but nothing goes to Z. That's also okay. They don't have to map to everything. All the stipulations about a function are on the set we're mapping from. So if we're mapping from A, that's where all the conditions are on, is A. So if we were to look at the relation 1 comma Y, 2 comma Z, 3 comma W, 1 comma X, it's not a function, because it would try to map 1 to Y and 1 to X. So what is f of 1 in this case? Well, it doesn't make sense because it's trying to go to Y and X. And similarly, the relation f equals 1 comma Z, 2 comma X is not a function, because in this case, what is f of 3? Well, there's nothing because f of 3 isn't in this set. So there's no definition of what it maps to. So in this case, f is not a function. But let's look at something, instead of just making up these two small sets, that's related to real numbers, which is probably what you're most used to seeing. So let's go from the real numbers to the real numbers. So this is a map. F goes from R to R. And the relation is going to be x comma x squared. So this relation, x comma x squared, is saying f of x equals x squared. That's the function. So that's how you're probably used to seeing the notation. Okay, I've got it written right here in the lesson. So f of x equals x squared. So f of 2 is 4, f of negative 1 is 1, f of 5 is 25. And no matter what number you pick in the real numbers, you can plug it in this function and get a number out. So in particular, there's exactly one pair for each number. So this f of 2 equals 4, it means that if you start with 2, you're going to get 4. That's the only pair that starts with 2. Negative 1 is paired with 1. That's the only pair that starts with the negative 1. So f of negative 1 is well defined as being only 1. There's no number that's missing whenever we put it in, that we would say it's undefined, and there's no number that has two different values. So f of 2 is always 4, it's not going to be 4 and some other thing. Notice that f of 1 also equals 1, that's not a problem. So we can map different numbers to the same number, that's fine for functions. And also nothing maps to, for example, if I try to say f of x equals negative 1, there's no x. So I guess you could say DNE if you want, it does not exist. What I'm saying is this x doesn't exist because we're mapping from the real numbers. Now, if you put in complex numbers like I, you could find an answer, but f is not defined on the complex numbers, it's in the real numbers. So for a function, it doesn't have to map to everything, and it can map to the same thing more than once. Those aren't the conditions. The conditions are on what it's mapping from. So if it's mapping from R, it means that for every R I plug in, there's exactly one output. So f of x equals square root x is not a function on the real numbers R, because f of negative 1 equals y doesn't have an output. So it's every number should have exactly one output. The function would work if I went from 0, infinity, only the positive numbers, to R. Then that's a function, as f of x equals square root x. Because for every input now, I would have exactly one output. I could put in f of 1 and get 1. I could put in f of 2 and get square root 2. So the input and output is important.